The Scanning Electron Microscope. This is the first of a two-part series on the background and operation of a scanning electron microscope for Nano 120A. Scanning electron microscopes offer several advantages over conventional light microscopes. One advantage of an SEM is its improved resolving power. This resolving power, or resolution, can be described as the smallest distance between two adjacent features on a sample at which the microscope can distinguish them as two separate features. A second advantage of the SEM is its improved depth of focus. This is the distance between extreme points, or rather high and low points on a sample that can remain in focus over a range of magnifications. The major components of a scanning electron microscope are depicted here. The electron beam originates from a fine filament wire or crystal held at high voltage. When heated, the electrons are emitted through a process called thermionic emission, and they are accelerated by the presence of a positive anode plate. The electrons are passed through the core of a condenser lens that consists of a series of copper coils or windings that control a magnetic field that focuses the electrons into a beam. The second lens, the objective lens, focuses the beam to the final spot size on the sample and rasters that beam across the specimen in an XY pattern. The sample sits in the sample chamber surrounded by a variety of detectors that collect signals from the electron beam interactions with the sample. The collected signals are used to form images of the sample on the CRT or computer screen, or for evaluating the sample's chemical composition. The signal intensity coming off the sample and the resolution of the instrument are dictated by the beam current and the beam size, respectively. Scanning electron microscopes can collect electron signals, for example, that are generated from the interaction of the electron beam with the specimen, and display those signal intensities on a CRT or computer monitor, such that there is a one-to-one correspondence between the point on the sample creating the signal and the point on the monitor screen, called a pixel. The scanning rate by the beam on the sample is synchronized with the refresh rate of the monitor to provide this one-to-one correspondence between the scanned area and the image on the screen. The intensity of the signal in the image on the monitor viewing screen depends on the amount of signal collected from the corresponding point in the raster scan from the sample. These differences in signal intensity generate the contrast in the image. Contrast is related to the difference in intensity between 2 points, so the entire grayscale from black to white and every gray shade in between appear in the image. Some of the events that can occur to produce signals from a specimen due to its interaction with the electron beam are shown here. When the incident beam impinges on the specimen, backscattered electrons can result. These are the incoming beam electrons that experience a Coulombic interaction with the positive nucleus of the atoms in the sample and bounce back or scatter backwards without any loss of energy. Another signal obtained from the electron beam interaction with the specimen are characteristic X-rays. These are released from an atom in the sample as a result of a relaxation event that occurs after the incident beam electron removes or knocks out an inner shell electron from an atom in the specimen. Other electron beam specimen interactions include Auger electrons, secondary electrons, and visible light. The ability to detect any of these signals shown here depend on the types of detectors the microscope has to pick up these signals. In this class, the two signals for which our SEM is equipped to detect are the backscattered electrons and the characteristic X-rays. As mentioned, backscattered electrons are created when the incident electrons in the raster beam scatter off the atomic nuclei in a sample. These electrons lose no energy in the process, and their probability of scattering from a particular element depends on the atomic number of the element. Higher atomic number elements have a greater probability of scatter, that is, produce more backscattered electrons than lower atomic number elements due to the larger nucleus for scattering on the higher atomic numbers. This is shown in the graph at the right. This difference in signal intensity that results from the relationship between the number of backscattered electrons generated and the atomic number of the element present in the sample contributes to a type of contrast called atomic number contrast. Backscattered electrons carry important atomic number information for a sample. The detector for backscattered electrons should be positioned to optimize collection of the backscatter signal. In this diagram, for a flat sample surface, the number distribution of backscattered electrons is represented by the solid circle. One can see that as the angle phi shown between the position of the detector and the incident beam increases toward 90 degrees, the number of backscattered electrons detected for this flat surface decline, as represented by the points of intersection of this solid circle with the dotted semicircles. Therefore, for an electron beam incident on a flat surface or untilted sample, the most efficient position of a detector to collect the backscattered electrons would be within a few degrees of the incoming beam. As a result, backscattered detectors are placed directly over the sample to maximize collection of the backscattered signal. As mentioned, backscatter electrons can provide a type of contrast based on elemental differences in a sample, which is known as atomic number contrast. However, a backscatter detector can also be designed to provide some information on another type of contrast called topographic contrast. This is a type of contrast that results from electrons impinging on rough or tilted surfaces and is a result of the trajectory that the electron takes to the detector. In this image, we show a light analogy as to how topographic contrast works. For light rays incident at an angle on a non-flat surface with rough surface features as shown in the left-hand diagram, only those light rays that are reflected toward the observer at the top of the diagram will appear bright. The rays deflected away from the observer will appear dark. Such an unevenly illuminated surface reveals its topographic features as shown in the right-hand photo. Similar topographic information can be obtained in an SEM with a segmented backscatter detector design, where each segment can operate independently to provide several topographic options. These two figures shown here represent two possibilities of how a segmented backscatter detector can provide surface roughness features for a specimen. On the left, turning the left side segments on and the right side segments off provides topographic information along the x direction. Another view of this sample along the y-axis can be obtained by turning the front half on or off with respect to the back half of the detector, as shown in the right-hand image. In either case, only those electrons scattered into the view of the portion of the detector that is on will appear brighter, while the regions of the sample scattering toward the detector segments that are off will appear darker. Finally, another signal of interest which is useful for the evaluation of chemical species in a sample is the characteristic X-ray. The sequence of events producing characteristic X-rays are shown in the figure on the left. An electron from the incoming electron beam of the SEM knocks out an inner shell electron from an atom in the sample. After the electron is removed, the atom is in an excited state that results in an electron dropping down from an upper energy level into the vacated space. This electron transition results in an X-ray photon being released with an energy equal to the difference in energies between the levels from where the upper level electron originated and the lower energy level into which it dropped. These X-rays are called characteristic X-rays because their energy is unique to the energy level differences in the element creating it. Therefore, by collecting the X-rays with an X-ray detector, sorting them by energy, and counting the signals per energy, A histogram showing the intensity of the signal as a function of energy can be displayed as shown on the right. This technique is known as energy dispersive spectroscopy, or EDS, and is used to not only identify what elements are present, but also to quantify the amount of that element that produced it. Thus, energy dispersive spectroscopy is both qualitative and quantitative. Part 2 of this video will provide a demonstration of the scanning electron microscope capabilities.